All right, so first semester, and I already said it, but this is basically a comprehensive outline, as it says in the title there, meaning it's everything you should study. When I made this review sheet, I was looking right at the exam, and even the order is pretty much in order on the exam. Does it mean every little thing is on here? No. Does it mean just because there's one bullet, like chapter 1 through 4, number 1, that could probably be one question, but if you look at number 2 here, 5 divisions of chemistry and characteristics, of course I could get 5 questions out of that. So you got to make sure you know your stuff really, really well. And then this, it doesn't cover everything in detail. That's what I'll try to give you now, is a little bit more detail to work with. I'm not going to go into extreme detail with it, but so whatever I write down, I would say you should probably be writing down as well, and maybe even more. So the first thing here, chemistry, composition of matter and changes it undergoes. Just know the definition of chemistry. That was like the first day. The 5 divisions of chemistry, bullet 2 here, and characteristics. We need to go through those 5. You need to be aware of all 5. So one of them, I'll just go through a list. The order doesn't really matter. One could be analytical chemistry. And with analytical chemistry, I'm going to try to give you just real fine points to look out for. Look for that root word, analyze. You're analyzing things. And analytical chemistry will often have a lot of math involved with it. Okay. So analytical chem will often have a lot of mathematics, or you're figuring things out, or you're determining the composition of a sample of ore like C&H did here with the copper. So analytical, one that's a little tougher, and if it doesn't seem to fit the other 4, go with physical. But physical, you're looking at behavior of chemicals, behavior of compounds, behavior of plastics, how they respond to stress, things like that. There's biochemistry. I'm just going to say bio, but there's biochemistry. And biochemistry, you need to start thinking about things that are living, okay? Or you're looking at processes of living things, like a new insulin drug for diabetics would probably involve some biochemistry. All right. And then there is organic chemistry. So organic chemistry, one big thing, carbon, C. Organic chemistry is the study of compounds containing carbon. And then the opposite of organic is inorganic. And inorganic without carbon. Okay? Compounds that do not have carbon. So there's our 5 divisions of chemistry that you need to be aware of. I'll ask a question or two on that. The scientific method, I have OHE here. That's the order of the steps. Yes, there's many different steps in the scientific method. I don't think it's a clear-cut method like a lot of textbooks say, but these 3 steps are important. So know I just put OHE for order, but first you make an observation. And after the observation, you form a hypothesis. And a hypothesis, I know a lot of teachers and scientists don't like the definition a lot of people give it, but it's an educated guess. I agree with that. It is an educated guess. You're guessing why something is happening based on some things you already know. And then the last thing is you run an experiment, or you test that hypothesis. Okay? And then, of course, you're going to get data, and you're going to analyze that data, look through it, and then you're going to go back through, make more observations, and run through that whole program again. Okay? So then we have theory versus law. For theory versus law, just make sure you're aware of the definitions there. And I'm going to give you as simple a definition as we possibly can. I'll start with law. Law is considered to be fact, by the majority of people at least. Everybody, for the most part, agrees that what goes up must come down. That's the law of gravity. Okay? And also with law, a law is usually a short, and I'm just going to go slash, concise, that should be a C there, statement. So a law is often a short, concise statement. It's just to the point. Okay? Law of conservation of energy, for example. Energy is neither created nor destroyed. It's a law. A theory, it's not necessarily considered fact. There's a lot of evidence to support it, but it is a theory. And I'm just going to say it's usually a long explanation of why something might be or might happen. And there could be whole books on this, whole libraries of information on this, societies around this, okay? But not necessarily fact or agreed upon as fact. And then you have matter there. Pull this up a little bit. So matter, the solid, liquid, gas. And I have one more state there, that last state, plasma. We didn't really talk about plasma too much. I'm not too concerned about it other than realize it is the highest energy state of matter. But definitely know the order, solid, liquid, gas. Solid would be lowest energy, how the molecules are moving. The molecules in your desk and your pencils right now, they're moving, just rather slowly. Liquid, the molecules have a higher energy, so they're spreading out a little bit. And then the gas, I'm going to say high energy. You know, molecules are really moving fast, and they're moving far apart from one another. That's why there's a lot of space. And of course, plasma would be the highest energy if it showed up as a question, which it probably won't, just to be honest with you. And then characteristics in volume and shape. So solid, down here at the solid end, that has a definite shape. So the word definite or a fixed shape. So a definite shape and volume, meaning the shape and the volume of your desk is just constant. It's staying exactly the way it is. Okay. The liquid, let me make myself some more room here. So for the liquid right here, as far as volume, it has definite volume. If you have 100 milliliters of liquid, no matter what you do, you have 100 milliliters of liquid. Okay? But it does not have a definite shape, or you would say, I'm going to put slash, indefinite shape. For example, if you have a water bottle that has 16 ounces of water in it, and you pour it on the table, there's still 16 ounces of water, but its shape has changed. Okay? And then the gas, the last one, for the gas, it has both indefinite shape and volume. In other words, you could have 100 milliliters of a gas, give it more space, and it'll occupy that space. It'll expand to 1,000 milliliters. Or it'll change its shape. I could have a gas in a little cylinder and let it out in this room, and it's going to change its shape to fit the shape of this room. And then physical and chemical properties and changes rather. Just physical. For physical, be aware that there is not a change in composition. I'm going to put delta for change. That triangle means change, just to shorten it up. So no change in composition. I'm just going to say comp there. For example, if I take a piece of paper and I tear it, it's still paper. I changed its shape a little bit and stuff, but I didn't change that it's paper. A chemical change, on the other hand, has a change, or triangle, in composition. So a chemical change on a piece of paper, if I burn it, it's no longer paper. It's mostly just pure carbon. Okay? And a chemical change, you can't get back what you started with. A physical change, you can get back what you started with. So atoms versus elements versus compounds. Atoms, just know, are the simplest. So I'm just going to say simplest. For lack of a better word here, I'll say piece of matter. So for example, copper, the simplest piece of copper that you could have is an atom of copper. Okay? And then elements are represented by atoms. Okay? You could have elemental copper, but have it be more than one atom. You could have 1,000,000 atoms of copper and have it all be pure copper, but one atom is the smallest piece of copper you could have. And then a compound here. Compound is just a combination of atoms. They're compounded together. And usually they're in a defined ratio, like water, you know, is H2O. Okay? It's always 2 hydrogen, and it's always 1 oxygen to be water. So now number 8, it says know the symbols and names for common elements on the very last page of your textbook, table 8.3. And this is the one where I said there's going to be a lot of them there. I'm just going to turn to my textbook. If you got yours, you should probably turn there as well. You just open up the back cover and it's right there. And you look at it, and I know you want to say, oh, there's lots that we never even studied or anything like that. That's fine. I'm not going to add, I might ask one or two that might seem a little bit crazier, but many of those we have used. For example, just do a couple here. C. If it's C, carbon. Okay? I'm going to give you the ones that you should watch out that people confuse. So C is carbon. Watch out for that one. And a common one that I probably might throw on the exam just to see who's looking at the details is Ca. Ca is not carbon. Ca is calcium, of course. Another common misconception, here's an example question. What is the element symbol for sodium? What do a lot of people pick? That. S is sulfur, of course. Sodium is the Na. Another one to watch out for is what is the elemental symbol for potassium? A lot of people will pick this.
K.
P, yeah. Which is phosphorus. Okay. So P is phosphorus, but potassium you have to know is K. All right. So watch out for those. And then there's some other oddball ones like W. W is in the list. W is tungsten. We have used this one in the past. PB. PB is lead. Hg is in that list, I believe. Hg is mercury. Okay. But I am going to go with a number of the ones that I feel you should know, like N is nitrogen, O is oxygen, ones that we've used a lot. And then I am going to try a few like these, the Na. So I could ask the question, what is the elemental symbol for sodium? Or I could say the elemental symbol S is for what element? And you'd have to pick sulfur in that case. And then a chemical formula, number 9 here, it indicates which elements and proportions. I already mentioned this a little bit, but H2O is an example of a chemical formula. It represents the compound water. And then when I say which elements and proportions, so I could have a simple question just like this. The chemical formula H2O means what? And have 4 answers. Well, it means how many hydrogens? There's 2 hydrogens. So after the element is always your subscript, and there's 1 oxygen, okay, if it's by itself. So maybe a question, just one it'd probably be, but a simple question like that, and you want to get as many simple questions as you can. Chemical reactions here, just be aware of what a chemical reaction is. It's when atoms are rearranged, but not created nor destroyed. You're not destroying atoms, you're rearranging them. Even in the biggest explosions, atoms are just being rearranged into new things. Examples of chemical versus physical changes. Be aware of a couple because I'll ask some questions. Which of the following would be a chemical change? You cut a piece of cheese, you freeze a piece of cheese, you melt a piece of cheese, or a piece of cheese spoils, which means it rots, which means it was changed. You can't get it back even if it spoils. If you could do that, you'd be a very wealthy person. Okay, but you can't. So be aware of those. And then number 12, the units of measure, SI base units. There is a table with the symbols and everything that I have listed for you. You want to make sure you go look at that table. So we're looking at number 12 here. So SI base units and the symbols and all that. There's a couple odd ones, like what's the SI base unit for the amount of substance or how much stuff you have? It's the mole. Okay. Actually, let's take a look at page 63 here, real quick. You want to be aware of them. So example, like they have their length, know that length, the SI base unit is the meter. Volume is a derived unit, that'd be good to know. It's a cubic meter. Mass is the kilogram. Mass is a common one that people will say the gram, but it's the kilogram. Okay. Time is second. So just be aware of that table, look through it a bit. I'll ask maybe a couple questions on that table. 13, very important because it's used potentially throughout the exam and definitely into next semester quite a bit here. So scientific notation, know what the term coefficient means, and know that that coefficient must be right here, greater than or equal to 1. and less than 10. And then know what I mean by the term power. I'll give you an example here. And know what the difference is between negative versus positive for those powers. So an example of a number written in scientific notation would be 1.0 times 10 to the negative third, for example. Okay? So 1.0 times 10 to the negative third, just a simple number. I could ask a simple question. What's the coefficient in this value? That's your coefficient. So the coefficient is the number up front. And that number must be, again, between 1 and less than 10. And then this is your power. Okay? So know that it's a negative power here. Know what negative means. Just be aware that negative means it's going to be a number when you write this out in standard notation. It's going to be less than 1. Or you can think of it, I've been saying, or it's going to be a small number. If it's positive, it's going to be greater than 1, the overall value, or the way I've been saying it, it's going to be a big number. Okay? So like 1.0 here times 10 to the negative third, it's going to be either 1,000 or 0.001, and it's going to be the 0.001. Okay? So know how to deal with this decimal as well. And if you're struggling, write on the exam. You get to write on the exam. Just write around each question. Just be figuring things out. So I'm just going to write, I have 1 in here. And right now the decimal is right there. I need to make this number smaller. Okay? So right now these zeros don't really mean anything. That's okay to put them there. This is still the number 1. Okay? But negative means this number needs to be smaller. And it needs to be 3 times smaller. So there's 1, 2, 3. So that value in standard notation, 2 zeros, is 0.001 or 0.001. If that were a positive 3, I'd have the 1. I know I need to make it bigger, so I need more zeros. So I have 1.0 right now, but I move it 1, 2, 3. So it'd be right there. So it'd be 1,000, your answer. So just some simple things like that. Know how to multiply, divide, add, subtract in scientific notation. And the big thing there is, let's say you had the number 4.5, because there's going to be a little bit of dimensional analysis on this exam. So 4.5 times the factor, let's say involved, let's say this was meters and we had to go to nanometers. All right. So you'd say, okay, what's bigger? The meter's bigger, put a 1. How many nanometers in a meter? It's a lot, so it's 1 times 10 to the 9th. You're going to have to know your prefixes. We'll get to that in a bit here. So when you enter this in your calculator, this is what this number bullet 14 bullet is talking about. You do 4.5 times in your calculator, and then 1, and then this is what you got to watch out for. You would not hit times 10 in your calculator. You would press the EE button. Okay? And then you would do 9. So in your calculator, that would look like 1 EE 9. And this EE button means times 10. Okay? So 1 times 10 to the 9th written right here. Calculator, it's 1. Press EE 9 or E. Okay? So now, quantitative versus qualitative. Let's take a look at that. Pretty easy. Look for the root words in those. Pull this up a bit. So quantitative versus qualitative measurements, a problem. You should not get this one wrong, hopefully. Look for the root word there, quant. Okay. So quant, you're looking at a quantity. In quantities, you're thinking numbers. If it's a qualitative measurement, look at that root word again. Just look for the clues on the whole exam to try to pass through this. In qualitative, you're looking at some quality, which is not having a numeric value to it. Okay, shirt is red. Quantitative measurement would be, I used a spectroscope and found out the wavelength was 700 nanometers for your shirt. That's quantitative. Accuracy versus precision, easiest thing to do. Easiest thing to do with that, if you're struggling with it on a question, is just think back to what we did in lecture. If you had a dartboard, so you're usually aiming for the bullseye in a dartboard. Okay. If one person threw 3 darts, one was here, and one was there. Is it accurate, precise, or neither, or both? Well, you're going for the bullseye, you know, right here. Okay, you're not close to there. The average maybe is getting out, but nothing's even close. I would say that's neither. If you wanted a measurement that looked like it was precise, so you're going for the bullseye, and you get a grouping of shots that are, say, one here, and one there. It's not very good accuracy. You're not getting where you should be getting, okay? But that's a precise grouping of measurements because they're all close to one another. And then a third scenario, and this usually works for anything that I'll ask on the exam level at least. The third scenario, let's say you get a shot here, a shot kind of right in the bullseye, and then another shot there. Pretty darn accurate, okay? You're getting at least on what you're trying to hit. And I'd say that's precise as well. So now we're getting into significant figures here. When I say estimated digits, so an estimated digit, we'll try to keep this as simple as possible for exam. Let's say you have a measurement that is 102.78 centimeters, inches, whatever it might be. Okay? With significant, I'm going to talk about significant figures along with this estimated digit here. So significant figures definitely know a definition. So a significant figure definition, probably the simplest definition I can come up with is all values, and this isn't a measurement, all values known for sure or with confidence, I'll say for sure, plus one estimated digit. Okay? So everything you know for sure plus one estimated digit. So I measure the width of this screen and I find that it's just over 1 meter. Well, how much over 1 meter? I say, oh, it's 1 1/10. Okay? So your last digit is always your estimated digit. Okay? So here, somebody estimated that, the 8, or the hundreds position. 100. Okay? So now there's a bunch of examples here. I'll clean this up. And you want to make sure, I do ask quite a few just simple questions on significant figures on the exam. So be ready for it. I think there's at least 5 or 6, half a dozen, where I give you a number just like a number 18 here, 19, and 20. Give you a number and you just have to report how many significant figures. Or I say, which of the following has 3 sig figs? Okay. So this, it's the zeros that are tough. There's no zeros in 1 centimeter. That is one significant figure. There's just one non-zero. The 1.0, the next one, zeros that are after a non-zero, like 1 here, and after a decimal, anywhere after a decimal, are significant. So this would be 2 significant figures. Okay? The 0.1, well, that 0 is doing nothing. Don't really need it there, so don't look at that one. 0.1, that's just one number, so it's 1. The 0.01, again, that 0 out front, you could write the number without it and it'd still be the same. This 0, right there, as best as I can point at it, that is a placeholder. Okay? Placeholders are just getting you out to where there is actually something to measure. So whatever this was so small that there's not even 1/10 of a centimeter. You're not getting a measurement until the 100th position. And then that 1 counts. So that's one significant figure. The 0.010, again, this first 0, you don't need it. The second 0, that's a placeholder. This 0, I just covered up my decimal there, but this 0 that I'm pointing at there is after a non-zero, and somewhere it's after a decimal. So this 0 at the end is going to count. So that's 2 significant figures. 0.101, the 0 in the middle, watch out for those. Not a very technical term, but we call them a 0 sandwich. They count. They're good. So that has 0.101 has 3 significant figures. 10 centimeters. This 0 in the 10 centimeters. It's after a non-zero, okay, but is nowhere after a decimal. There's no decimal anywhere that it's after. So that 0 does not count. Somebody really rounded that number. So that's 1 significant figure. The 10.1, there's a 0 sandwich, so it's going to count. That has 3. The 10.0, okay, 10.0, is this 0 after a decimal? Yep. Is it somewhere after a non-zero? Yep. Which makes this 0 end up being significant as well then. So that has 3. The 11.0, that 0 again is after a non-zero and it's somewhere after a decimal. It has 3. 11.1, about as easy as you can get. No zeros to worry about, so it's 3. 11.01, 0 sandwich, it's going to count. That has 4. 11.010, you have a 0 sandwich, that will count. And this 0, it's after a non-zero and it's somewhere after a decimal. Okay, as long as there's a decimal somewhere, so it counts. That has 5. 10.001, big 0 sandwich right there. They all count. That has 1, 2, 3, 4, 5 significant figures. 0.1, seems like we had this already. Yep. 0.1 is just 1 sig fig. The 0.01, I think we had that one already. That is 1 significant figure. 0.010, the 0 on the end. It is going to count because it's after a non-zero and somewhere after a decimal. So that 0 counts. The 0 up front here before the 1 does not count. It's a placeholder. It's after a decimal, but is nowhere after a non-zero. So that has 2 sig figs. 60 minutes, watch out, I'll throw a couple of these because I'll get you going fast on the exam, feeling good, and I'll throw something like this. Okay, so 60 minutes. That and 60 minutes per hour are kind of hard to keep separated. I'll talk about this one first. The 60 minutes in an hour. There are exactly 60 minutes in 1 hour. No more, no less. Not 60.1, nothing like that. So this is an exact quantity. So that's infinite number of sig figs or unlimited. So there's the sign for infinity. Back to the 60 minutes. Could you have 61 minutes? Yeah. Could you have 62 minutes? Yeah. If you're timing something. Or 60.7 or 1 or whatever. Yeah. So that only has 1 sig fig. 60 people. Count the number of people on this floor right now. There's 60. No more, no less. And it's exact quantity. Usually, unless it's statistics you're doing. So that's infinite. 60.0 minutes, it was timed. Okay, that's 3. 6.60 minutes is 3. Those zeros are counting. So if you struggle with sig figs, that's all I can go over now, but come see me and we can go over some with you. So number 21, significant figures and calculations. Make sure you know what these terms mean because they're used in the questions sometimes. Sum means add or plus. Difference means subtract. Okay. Product means multiply. Quotient means divide. And we've worked with significant figures. So calculation, a simple calculation. Let's say it's 2.0 times 3. And your calculator would say 6.0 more than likely. How many sig figs can you have when you're multiplying or dividing? Your answer has the same as the least number of sig figs in the calculation. So this has 2 sig figs. This only has 1. Your answer would have to have 1. So this would be 6 as an answer. Okay. When you're adding and subtracting, let's say you have 2.1 plus 5. I mean, it's simple, but we're not going to go into the details like we did when we talked about it. But on a calculator, it would say 7.1. When you're adding or subtracting, so say this is an adding, when you're adding or subtracting, your answer can be no more precise than the least precise measurement, or no more decimals than the one with the least number of decimals. This has 1 decimal, this has 0 decimals. Your answer can only have 0 decimals, so you'd have to round that to 7. Okay? Again, if you struggle with that a bit, come see me. So 22, the metric system. The metric system that's going to be very important on the exam, really look at this carefully and make sure you're ready for it. So it says units and prefixes, and I say exponential, fraction, decimal form. Go to page 64 in your text and we'll look at a few things there. It's table 3.2 and 3.3. So the table at the top of the page and the bottom of the page. And there's a couple ways to look at this. I'll look at the bottom of the page first. So there's kilometer, decimeter, micrometer, nanometer, all of that. They're just giving you comparisons there. But the top table 3.2, mega, kilo, deci, milli, micro, nano, pico. You need to be very, very aware of all of those. And when I say exponential form, that means it has an exponent, fraction, and decimal. I'll show you what I mean here. So the first thing is I'll start with centi, and I'll kind of build the table here. You should be able to build this table on paper, okay, your own way. So centi, like in centimeter or centigram, okay, it means small. Centimeter, centigram, they're smaller than their base unit, smaller than the meter, smaller than the gram, okay? And you can see there the symbol, of course, be aware of, it's C. So when I say centimeter, it's cm, or centigram, you're looking at the C. Okay, that's your prefix. So the centi part says 100 times smaller than the unit it precedes. That's good to understand that meaning. The fraction is good to understand. I usually start with the exponential form, and I mean this. So 10 to the negative 2. Okay. We talked about this in lecture, but if you have a negative exponent, that means it's going to be 1 over whatever your value is here. So it's 1 over 10 squared, basically. And then 10 squared is 10 times 10, which is 100. So centi means 1/100th. So I start by remembering this first. So centi means 10 to the negative second. Okay. And know the order as well. Then milli, symbol would be M. So like millimeter, mm, milligram, mg, and it's a lowercase m. Milli is going to be 10 to the negative third, or 1 over 10 to the third, which equals 1 over 10 times 10 times 10, which is 1,000. So it's 1,000. Or a millimeter is 1/1000th of a meter, or a milligram is 1/1000th of a gram. Okay? And you can see next on the list there is micro. So micro, I'm going to do a symbol out front here. That was that flying seagull thing, that funny cursive looking M. Micro is getting smaller yet. So micro is 10 to the negative 6 you need to remember. Or 1 over 10 to the 6, or 1 over a million. For me, the biggest thing is this exponential form, and with you guys, because you can use it in calculations that we're going to do throughout the year at various points. You can see next on our list is nano, and that's where we stop. You don't have to know pico, although you can easily get it. So nano was the one, it's really small, so it's 10 to the negative 9th. Okay? And it depends on how you use it, which we already used it once today. So how many nanometers in a meter? There's 10 to the 9th nanometers in a meter. You got to be careful on how you use that one. Okay? And then above centi, deci you should be aware of. Not very common. So deci is 10 to the negative 1, or 1 over 10, or a decimeter. Okay, is 1/10 of a meter. And then going up off of deci, I'm going to have to go over here a little bit. So then up off of deci you can see kilo, like in kilometer. So kilo equals 10 to the third. So it's not 1 over 10 to the third because it's positive this time. So 10 to the third is 10 times 10 times 10, which is 1,000. So like a kilometer, K is the abbreviation or the prefix. Kilometer is 1,000 meters. Or a kilometer is 1,000 times bigger than a meter. Or a kilogram is 1,000 times bigger than a gram. And then the last one, mega, with a capital M. So capital M is the prefix. Mega and micro I kind of remember together. Micro was 10 to the negative 6. Mega is opposite. It's 10 to the positive 6. Okay? Mega, it's huge. its positive exponent. Okay? So now mass versus weight. So know that mass does not depend on location. No matter where you find the mass of a 1 kilogram object, it's always going to be 1 kilogram. And then mass, as far as definition, it might show up. It's the amount of matter. That's about as easy of a definition as we can write. Amount of matter, how much matter is in something. Weight. Weight does depend on gravity. Okay, so it does depend on location. Your weight on Earth is quite a bit more than it is on the moon. So be aware of those. Density. Know the formula for density. Okay. So the formula for density, you're starting with the D. Density equals mass over volume. And usually we write it as M over V. So density equals mass over volume, or M over V. And the mass could be anything from kilograms to grams to whatever, but usually it's grams. And often the volume is milliliters. Okay? So be aware of how to use that. So just a quick example problem. You have an object. It has a mass of 6 grams and it occupies 30 milliliters of space. What is its density? You would plug in 6 into the mass right there, and you would plug in the 30 into the volume, and then you would divide it out. Okay? So be able to do that. And you should be able to, I should erase that. You should also be able to manipulate that equation to get whatever you need given any information. So for example, say you have density equals mass over volume, but I have the mass and the density, so I want to find volume. How do you get volume isolated? How do you get it on its own? You'd multiply the equation by V on both sides. So V would cancel here. So you'd have mass equals the density times the volume. Okay? Or again, start with that equation, density equals mass over volume. And you have the volume and the density. Okay? So I'll usually say, okay, if I want mass, the easiest way I can see it is I know if I do this, and whatever works for you, I have mass equals density over volume. I say, no, I want the volume. How do I get density out of here now? Divide by D. So then you divide by D. So volume equals mass over density. Okay? Whatever way ends up working for you. Specific gravity. Be aware of that formula as well. So specific gravity is kind of like I showed you when I had the urine sample. I want to know what is its specific gravity. Just be aware of the definition. So specific gravity, or SG, it's often abbreviated as, is the density of, I'm just going to say object, or whatever you're interested in, like the density of that urine, over, usually it's the density of water. Okay? You divide those two. And the density of water, its mass over volume, is, there's 1 gram per milliliter. The density of water is 1. So if you had a milliliter of water, its mass would be 1 gram. At 4 degrees Celsius at least. It changes a little bit with temperature. So temperature, be aware of the 2 scales here. Celsius, abbreviated C often, or degrees C. Kelvin, it's usually just K, no degree symbol on it. And then be aware of the definition for Kelvin, or how do you convert to Kelvin given Celsius. So Kelvin equals however many degrees Celsius there are plus 273. Know that formula. There'll probably be one question just using that formula. If the temperature is 100 degrees Celsius, what is it in Kelvin? It'd be 100 plus 273. I might say the temperature in Kelvin is 100. What is that in Celsius? Write down this equation to get Celsius. Subtract off the 273 here. 273 minus 273 is 0. You have to do the same thing to the other side. So degrees Celsius equals Kelvin minus 273, then just the opposite. So 27 then, I have measuring actual items using measurement instruments correctly, estimating measurement correctly, reporting measurement correctly in units and all that. So it says be ready to go into the lab, measure the length of a line on a piece of paper. So you need the right sig fig. So you'd measure everything you know for sure plus one estimated digit. Okay, so maybe I'll look at that Monday with you a little bit more. But also I could have you go into the lab and I would say, here's an object, a marble, find its density. Okay, so a marble is a sphere. It's not easy to measure the volume of that. How could you measure the volume of it? Take a grad cylinder, fill it with 10 milliliters of water or 20 or whatever, drop the marble in there, the water will rise up, that's your volume. Okay? You might want to make a note about that on how to get density or volume of an irregular shaped object. So it's called water displacement. That could be a multiple choice question as well. You use water displacement to find the volume of an irregular shaped object. And again, that's where you take a grad cylinder, put 20 mils of water into it, or some measurement you know, drop the item in, let the water rise up, see what the difference is, and that's your volume. So we're going to use all our time here because there's a lot of things to cover. So 5 and 28, chapters 5 and 28. 5 is about the atom, 28 is getting into the nucleus of the atom and nuclear chemistry. So the atom, just know it's the smallest representative particle that you can have. Okay? And an atom, of course, includes protons, which are P plus or positive particles, neutrons, which have no charge. Those are in the nucleus. Which I'm talking about right here. Okay? So protons and neutrons found in your nucleus. So overall, there's a positive charge in the nucleus. And then your electrons are found flying around. Okay? So that's taking care of subatomic particles as well, number 4. Relative sizes with that and location. So protons and neutrons again in the nucleus. Electrons are in the, I really should say electrons in electron cloud. You have to realize that it's a cloud. It's not like a container that they're found in, like the nucleus is thought of. Okay? Sizes, know that protons and neutrons are both 1 atomic mass unit in size, or 1 AMU. We talked about AMUs before. And then realize, and I don't know that I'll ask the specific numbers, but the size, the electron quite a bit smaller. And the electron is 1/1840th approximately AMUs, so it's about 1/1840th the size of a proton or a neutron. Democritus and Dalton, just know that they're the first people that really talk about the atom as an idea. Democritus, know that he was the first, about 400 BC, started talking, came up with the word atomos, which meant cannot be cut any further, or not to be cut. Meaning you're at your smallest particle that you can get. Dalton was in the 1700s, late 1700s. He was kind of the person that brought it back to the forefront. Good 2,000 years later. And then started a revolution with chemistry a bit. Nucleus we talked about. Subatomic particles and their sizes and locations we talked about. Standard notation for an element. So number 5. 5 is very important. Everything's important here, but I'm just saying that I know there's some questions with this. So 5, standard notation for an element. It's numbers of protons, neutrons, and electrons. And this comes off the periodic table. So here's the symbol we used before. We said X. I'm going to write it down here, actually. So we said X, AZ, or AB. It could be YZ, it could be anything, but X is your chemical symbol. So like sodium, carbon, C for carbon. Okay. A and Z, you have to be careful with these two because you can switch them around. But A is often your mass number. And your mass number includes the number of protons and neutrons together. Okay. And then Z, or the lower number, is often your atomic number. And your atomic number just includes the number of protons. Okay. And then remember that if you were to subtract mass number minus the atomic number, what would you be left with? That would be your protons and neutrons together, minus just your protons would leave you just with the neutrons. So you could tell how many neutrons are in the element. And at this point, 2 months ago, the number of protons matched the number of electrons. Okay? So an example, let's say this was, we'll go with a simple example, C12-6. Okay? So the element is carbon. There are, according to this, a combination of 12 protons and neutrons. You don't know exactly how many, but you know this is the number of protons. And then you know you can subtract the two, there must be 6 neutrons. Okay. Isotopes, know that definition. I'll probably just ask it in definition form. So an isotope. Isotope are elements, or the same element. Let's do this. Same element. And you should know what determines your element. So I'm going to say determined by number of protons. So if you have 6 protons, for example, carbon, no matter what. 7 protons, nitrogen, no matter what. So I'm looking at the atomic numbers on the periodic table. The big blue numbers on the upper left. Okay? But isotopes are going to be the same element. They're going to have the same number of protons. I'm going to say comma, but different numbers of neutrons. Okay. AMU, we talked about it a little bit, but know what the symbols stand for. That means atomic mass unit. Okay. So now we're getting into the periodic table. And that's where I'm going to stop. And we'll continue on tomorrow.